We were provided with a battery, screw, wire, and a magnet and set the task of creating a motor for our first physics lab. Initially, we had no idea how we would be able to create such a thing, but later realized that this lab is asking us to examine the conversion of electrical energy into mechanical energy, thus creating a motor. Our lab consisted of 5 attempts in which we created a motor and examined its properties. Going back to when we had no idea what to do, we attached a magnet to the bottom of the battery and connected both battery poles with a wire. This caused the wire and the poles to heat up and the wire started smoking. We noted that electricity was flowing, but besides the potential fire hazard, we were no closer to producing a motor. We wanted a definition of a motor, so we came to the conclusion that something needed to spin from the electrical current. We created a preliminary drawing of a motor on the whiteboard. When experimenting with the equipment given, we noticed any combination of the screw on the magnet didn't result in spinning when the wire was directly connected to the magnet. We learned that the screw can be magnetized when it comes in contact with the battery, sufficiently enough so that the magnet and screw will suspend from the battery when it is held up. The screw was hung from the negative battery pole. After this was successful, we experimented with touching the wire to the positive pole of the battery and the magnet. This wasn't successful when the wire was directly touching the magnet. It only worked when the wire was held slightly, about a centimeter, away from the magnet. This resulted in the screw rotating clockwise. We wanted to experiment with the same setup, but reversing the battery poles. The current flows in a new direction, which results in the screw rotating anti-clockwise. This is due to the electrical current intersecting with the magnetic field of the magnet in the opposite way. But using a slow-mo camera, we had at least a faint possibility of determining the frequency, Hertz, using the formula frequency equals cycles over seconds. The setup was as follows. The experiment was performed, the slow-mo video was taken, and then another phone slow-moed the slow-mo. The slow-mo of the slow-mo was 3 minutes of counting revolutions. This was the simplest way we could come up with. To adjust for acceleration and deceleration, when counting the number of revolutions of the marked magnet, one person counted for the whole period and the other counted halfway and doubled their answer. The first frequency given by the person who counted throughout the whole video reached the conclusion that there were 228 revolutions in 10 seconds of real-time footage. The second frequency by the person who stopped counting halfway through reached the conclusion that there were 240 revolutions in 10 seconds of real-time footage. This gives the average frequency as follows. The first example of mechanical movement resulting from electrical currents was noted by Hans Christian Ørsted in 1820, who noticed a compass needle was repelled by a live wire placed nearby. This later inspired Michael Faraday, who would attempt a conversion from electrical energy to mechanical energy with the simple structure of a wire suspended loosely with electrical current dipped in a pool of mercury with a magnet inside, dubbed the Faraday motor. This was an early example of a homopolar motor. A homopolar motor is a direct current motor that causes constant circular motion which creates a continuous rotation without the need for current reversal. To create a homopolar motor, the following elements are required: a source of electric energy, a method to transfer the electrical energy, a magnet, and something to rotate as a result of the current and the magnetic field. To magnetize the screw must enter the magnetic field of the strong magnet. Substances such as iron, cobalt, and nickel have electrons that mostly spin in the same direction, making these substances have magnetic potential. Assuming the screw given is an alloy, including mostly iron with some cobalt or nickel, the screw can be magnetized in order to successfully suspend from the metal battery. This allows the screw and the magnet to rotate as it suspends from the screw. Lorentz forces are described as the forces exerted on a charged particle moving with velocity through an electric field and magnetic field. If the charged particle moves through the magnetic field, there will only be a force when it is perpendicular to the field, but if the particle moves parallel to the magnetic field, there will be no force.